Okay, with 1 bit prediction accuracy, as we have highlighted earlier, that we might take as an example that the state 0 is referring to not taken. Not taken means the branch did not satisfy the comparison, and because of that, it will not be taken. If it is taken, we will refer to that as state 1, and I will say that a branch is taken means that if I'm doing as an example a branch equal, it has been satisfied the comparison, and that means that the next instruction will just be the branch address instruction. We also mentioned that if I am in the 0 state and then 0 states, meaning that my prediction is not taken. So in my code, as soon as I will see a branch instruction, I am assuming that it is not taken, meaning the following instruction after the branch, I will directly fetch that particular instruction, just the following one, not the branch instruction. But if, while I'm going through my code, if the next instruction or the next branch instruction is following whatever I have predicted, meaning it was not taken, then I will stay in my same state, because my prediction was not to take, and the branch that I am testing right now is not to take, so I'm still in my same state. However, if a taken come, then I will move to the another state, which is 1 in this case. Here is taken, and I will be in that particular state 1, which I am predicting a taking. So the next instruction, branch instruction that I will face, I would assume, or I would predict that it would be taken, meaning that it will satisfy the comparison. So this instruction after the branch will be the branch instruction. So when I fetch the instruction after the branch, I will go and fetch the branch instruction. But unfortunately, if the next instruction that I would be facing is not taken, is not taken. If it is not taken, then I will move to the 0 instruction. But if it is taken, then I will stay with my instruction. This is by analogy, as we have described earlier, that if you are dealing with persons, you might assume at the very beginning that they are good persons. If they have or they begin to behave as a good persons, they will stay in the same state. If they would behave with another behavior or bad actions, then you will move to the other states that you would assume or predict that they are bad persons. And the same apply also while you are in these particular states. And this is usually if we are not mature enough. And we have also mentioned that this is something similar to whatever all of us faced while we were kids. It's not mature algorithm. We can just shift right or left by just one interaction or one experience. So this kind of prediction might be helpful or might be a good criteria. As an example, if all of my branches are always taken, just one direction, or always not taken, or the taken are a lot greater than the not taken, or the other way around. Meaning that I am not facing the ping pong action. Ping pong action means that I'm not facing like taken, not taken, taken, not taken, taken, not taken. It's just like not flipping each time, because if it's flipping each time, so this means that I am going from a state to another state, and I will not ever stay in my same states, which gives me an indication that always my prediction will be wrong. Just to remind you why we are using a prediction. The answer that as soon as I am facing or I have a branch instruction, I know in advance, this is a fact, that I have to stall for one time after that instruction. Why? I need just one stall to decide which next instruction I should fetch. Should I fetch just the following instruction as an order of my code, or should I fetch the branch address instruction? I have to wait for one stall, at least. And because of that, researchers have already thought about an enhancement for that particular process. And then they said that, okay, let's predict. Let's predict one of the direction. And then if our prediction was correct, then I'm saving time. If my prediction was not correct, then I will still stall the one time that I have to stall if I didn't have any prediction algorithm. So I'm not losing anything more. However, I would like also my prediction algorithm not to face the same exact quality as the situation if there is no prediction at all. And that's why I mentioned here that if I have this simple prediction algorithm and I am facing the ping pong action, meaning it's just flipping each time, taken, not taken, taken, not taken, then I would be exactly the same as no prediction algorithm is used. Okay. So now we will move to a little bit a much more mature prediction algorithm, which is using 2-bit predictors. So it's not only 1 bit, it's 2 bits. So if it is 2 bits, I would assume that I would have up to 4 states, because with 2 bits, I can have 4 different categories. I can have 0, 0, 0, 1, 1, 0, and 1, 1. Shows you here that I can begin with prediction not taken, and if not taken come, I will stay in the same state. But if taken come, I will still stay in the prediction not taken. But as you can see from the color, that this is a little bit dark gray, this is light gray. Meaning it just gives me an indication that now my opinion begin to be ready to change to another direction. So I'm not completely sure that it is not taken as I am here. Now I am in another state that maybe it is not taken. But if another taken come, then I will move to the prediction taken state. And as you can see with this purple is light, as opposed to this purple, which is dark, because in these states, I just moved up to another decision, which is, yeah, it may be taken. But if another taken comes, now I already totally moved to the way that it is prediction taken, as you can see from here. But let's try to go over these things again by a little bit with more detailed explanations and examples. So this 2-bit predictor or prediction algorithm, as we mentioned, we have 4 states, 0, 1, 0, 0, 0, 1, 1, 0, and 1, 1. And I need to refer to a meaning to each of these states. I would say like 0, 0, I can refer to that as strongly not taken. I can refer to the 0, 1 still not taken, but instead of strongly, I would be weakly not taken. With the 1, 1, I am now strongly taken. But with the 1, 0, it is weakly taken in this case. So you can think of this by another meaning, that this is the prediction bit. And this guy, you can think of this as a convection bit, for instance. So if you look at that first column, is either 0 or 1. And you will see that both zeros is not taken and both 1 are taken. But this and this is just to state that if it is strongly or weakly, this or this is just strongly or weakly. It's just like the physical meaning behind each of the bits, if you will. Then I am now in this state, as an example, in the 0, 0, meaning that I am my prediction is now strongly not taken, or at the end it's not taken. So the next branch that I will see in my code, I would assume or predict that it is not taken, meaning my following instruction after the branch which I will fetch is just the following one. So if this is branch here, I will fetch that particular instruction. This means my prediction is not taken. I still don't know if my prediction is correct or not. This depends on the results of this branch that I would face. If my prediction was correct and this guy was not taken, as I would have already predicted, then I would stay in the same exact state, that not taken. I have assumed that that person is not good, and then the actions that I have received are not good, then I will stay in my same state. Still, that person is not good. But if my prediction was not correct, this means that I would move to another state. So if taken come, I will go to the 0, 1 state in this case, which is still also predict as a non-taken, but it is weakly not taken. But it is still predicting not taken. But I am a little bit now more mature. I have like aging more right now. I'm no longer a kid. I wouldn't like change my opinion from just one action. I need to see like at least 2 actions to begin to move to the other side. So you have assumed here that the person is bad, but good actions. Then you went to another state here and say like, okay, maybe the person is bad. I'm not totally sure right now. There is a probability that the person is maybe only bad. I'm not totally sure that the person is 100% bad, which gives us an indication when I am in this state that maybe by another good action, I would flip to another particular state. But if you went to that particular state and are not taken come, unfortunately, you will return back to the strongly not taken, because this was just like a matter of a chance that the person did behave in a good shape, but unfortunately, most or the highest percentage of the actions were basically in the other direction. Or also with here, the prediction actually, or most of the predictions are going in the other direction. But if you were here and the taken come, then you begin now to move to a prediction of taken, but weakly, but you already predict as taken. So that means that the next instruction that you will see as a branch here, you would assume that it is taken. So you will not fetch the next instruction. Instead, you will fetch the branch address instruction. This means that your prediction is taken in this particular case. But again, if not taken come, you will move back to that state. If taken come, meaning that the prediction is really correct, then you would move to the strongly taken case in this case. But if in the 1 and taken come, you will still in the good or in the mode that you are also taken. But if not taken come, you would move to the other side. It's exactly the same things as I told you with the situations in our case. If I am in that state that the person is bad but good action, so I will move to maybe that person is bad, then good action, or maybe the person is good, another good action, the person is good. And moving back and forth and so on through these states or stay in the same states depends on what is the action from the other side, or in our case here, what is the output of the branch instruction that you have in your code. So with this kind of states, let's take some examples and see like how that prediction algorithm is behaving in each of the case. Assuming right now that you are in the 0, 0 states, and this usually would be given because in any assignments, I may tell you like, okay, you are here right now, and then I begin to give you like some options. Or maybe you are here right now, and then I'm giving you some option. So as an example, I'm telling you that you are in this particular case, it's weakly not taken, and then a good action come, or a bad action come, or something. What would be the next state, and so on and so forth. So assuming right now that you are in this 0, 0 states, which as we have mentioned, is strongly not taken. And if it is wrongly not taken, what is your prediction? My prediction is not taken, correct? But if not taken come, so your prediction that the person is not good, and then unfortunately, not good action came, so your prediction was correct in this case, and the not taken come, so it will keep you exactly in the same state. So your next state in this case would be again 0, 0. Correct? Just move you again to 0, 0. Another not taken come, so this is exactly as you predict, and it will move you to the 0, 0 case, and so on and so forth. And the not taken come, then you will stay in the same things as you can see from here, and always your prediction is correct. How this is affecting my algorithm? Of course, this will reduce a lot the time consuming, because always my prediction were correct, and if all my predictions were correct, then I am saving more time. Correct? Let's assume another situation. I am now in the 0, 0, but unfortunately a taken come, so this means that my prediction was not correct. Because 0, 0, I have predicted that it is not taken, but the next branch that I have faced is taken. So my prediction was not correct. That means that I have to stall one time, because I went to fetch something that is wrong. Then I just flushed everything from the pipeline and went to get another instruction. So at the very end, I'm losing that particular one stall. But if taken come, as you can see from here, if taken come, it will shift me to the 0, 1 state. So the next state in this case will be 0, 1. Let's say assume that taken come, 0, 1 is predicting not taken. So again, your prediction is not correct. But as soon as I am here and taken come, I will move to the 1, 0 state in this case. And if taken come, this my prediction is correct. If another taken come, I will move to the, I will move to the 1, 1. If another taken come, then I am correct. As you can see from here, just by always taken, beginning from the same exact state. In this case, my prediction was 100% correct. In this case, my prediction was 50% correct. Meaning that in half of this time, I am doing good. In half of the other time, I'm still also losing the one stall. Also, we can begin from another states, or we can have even different situations. Let's take both of them. Let's assume that we are beginning from the same state, but then 0, 0, and then taken come. If taken come, of course, my prediction was not correct, but then I would basically, if 0, 0 and taken come, I am moving to the 0, 1. So now I will go to the 0, 1. 0, 1 predict what? Predict not taken, and the good thing that not taken come in this case, so my prediction was correct. But if I am here and the not taken come, so I went back to the 0, 0, so I will go to the 0, 0. But in this case, I have the taken come, my prediction was not correct, and then I will move to the 0, 1, and assuming not taken, so the prediction is correct, but then I'll begin to flip. So as you can see from here, assuming that the branch in your code that you will face have this same, have this same particular actions, for instance, that it is taken, not taken, taken, not taken, taken, not taken, taken, not taken, and so on and so forth. So you begin with 0, 0. So you will just like flip here. You will stay in this loop, which gives you an indication that half the ways your predictions are correct, half the others percentage your predictions would not be correct. So at the very end, you are gaining or saving half of these stalls comparable to the action if there is no prediction at all. Let's apply the same exact scenario, that taken, not taken, taken, not taken, taken, not taken, but you faced that while you were in another state. Let's say that you began with a state 0, 1, and you still have the same exact scenario, taken, not taken, taken, not taken. Assume that you know in advance what is happening, so it is like that. I'm telling you that it is taken, not taken, taken, not taken. And let's also discuss what would be the states and how much of the percentage of our prediction and so on and so forth. So if it is 0, 1 and then taken, 0, 1, as you can see from here, is not taken, but unfortunately taken come. So in this case, my prediction was correct. And if I am in 0, 1 and taken come, I am moving now to 1, 0. So now I am moving to 1, 0. But 1, 0, as you can see from here, it is taken. But unfortunately, not taken come. So I am in 1, 0, and the not taken come, I'm going to 0, 1. And of course, also my prediction was not correct. 0, I am in 0, 1 right now. 0, 1 means not taken, not taken. So this means that my prediction was not correct because the taken come, and then I will move to 1, 0 again, prediction not correct, and so on and so forth. So as you can see from here, that although in my code I'm facing, or that particular other case, I'm facing the same scenario, taken, not taken, taken, not taken, but here I began with a 0, 1 state, all my predictions are not correct. And if all my predictions are not correct, so this means that it will give me the same efficiency as exactly the same way if I were to decide that I wouldn't use any prediction algorithm. So the main reason of giving you all of these examples, to give you an indication that by using a prediction algorithm, we cannot guarantee that we will be always 100% correct, but what we can guarantee that we will not go worse than if you didn't use a prediction algorithm. Because the worst case scenario, if you use the prediction algorithm, is just to go back to the same scenario, that you will have the stalls, one stall after any branch instruction. But there is a chance that you can save some of these particular stalls, for instance. We have also another thing that we would like to highlight, that we have something called exceptions and another thing called interrupts. So at the very end, either exceptions or interrupts is just unexpected events that would require changing in my flow. I have something that might say, please either stop or go in another direction or solve the problem or something like that. So what is the difference between exception and interrupt? Exception usually always arises within the CPU. As an example, overflow, system call, undefined opcode. But interrupt is from an external input-output controller. It's something coming from outside, not from the CPU itself. But of course, in either way, I have to deal with them and I have to have a certain particular action trying to solve these kind of things. So it's just like we can think of these just like another form of control hazard. In the case of exceptions, which is inside the CPU, as an example, if I'm facing an R-type arithmetic overflow or trying to execute an undefined instruction, or there is any input-output device request. This is, I guess, for both exceptions and interrupts, since some of them are from inside and the others from outside. Or any operating system service request, or any hardware malfunction and stuff like that. All of these kind of things will create problems. So how to deal with such problems? There are different ways to handle such situation. So as an example, I may need just to stop the instruction in the midstream, just in the very middle. I have to stop executing the instruction and try to see what is the problem, and I will go there to solve it. Or maybe I will say, no, please wait until I finish all of my prior instruction before that interrupt, and then I'm coming back to you after handling all of these kind of prior instructions, as an example. You may also flush all following instructions, like any following instruction, just flush it right now, then let's handle this problem. Maybe I will set a register just to show why there is an exception. Maybe I will save the address of that offending instruction, and then I will come back to this particular instruction later on if the situation permits me to do something like that. Or maybe I will jump to a pre-arranged address. So this address will handle like these kind of actions through the exception handler code. As you can see from here, there are like different situations that we can handle the exceptions depending on the situation itself. From the software side, the operating system will look at the reason behind the exception and then we'll deal with it. But if we were to design things by ourselves, so this means that actually we have to build our code in order like to handle such situation. If an interrupt is coming, or if there is a problem, or if there is a malfunction, what would be the criteria in this particular case? So as we mentioned, the interrupt caused by external events is something from outside. But in this case, it is asynchronous because it happened anytime while the program is executed. I am executing right now, and then suddenly an issue came to me from outside. So this is basically might be, or usually would be, asynchronous. And then it may be handled between instructions, so can let the instruction currently active in the pipeline complete before passing control to the interrupt handler. On the other hand, if I have exception, sometimes we call it traps. This will be caused by internal events. And in this case, I might need to handle that particular instruction. So I must stop the offending instruction midstream in the pipeline and pass control to the operating system trap handler. And the program just may continue or it may be aborted in this case. Just to give you, again, a difference between the two particular differences between the external and the internal interrupts or exceptions in this case, by analogy, is in our situation. So assuming that there is an instructor, or you are the instructor of a class, and you begin to explain things to the audience. If someone suddenly raises his or her hands, so this is something is maybe not expected from you, and this is basically an external interrupts. And when you have these external interrupts, you may choose to handle that interrupt momentarily, or you also may choose just to finish the slide or two until you just finish whatever you are explaining, and then you will begin to handle your question or the questions or the interrupts in this case. And that's why we say, like, you may leave the instructions currently active in the pipeline complete. So you will complete before you answer that particular question from the audience, one of the audience, correct? It is the same exact scenario. How about in this case? How about if you have an internal interruption? With an internal interruption, you might not be able to do the same action as you have done with the external instructions. With the external instructions, as an example, you may choose to stop and answer, or you may choose to continue for a couple of slides and then answer that particular question. But with the internal interrupts or internal exceptions or traps, let's say, as an example, you have to cough, hiccup, sneezing. You can't stop it. You have to handle that particular exceptions or traps, and then after that, you would be able to continue whatever you are doing. You can think by analogy with something here the same. As we mentioned, then you must stop the offending instructions. You have to stop explaining the slides because there is a hiccup or coughing or sneezing. You have to stop it in the midstream and then try to solve the problem, and then going back to whatever you were in this case. So let's see, as an example, this issue here. The question is, where in the pipeline exceptions occur this kind of actions? So we have here a pipeline, and we are giving you like the issue here, and we are asking in which stage and if this is synchronous or asynchronous in this particular case. So with the arithmetic overflow, of course, I would expect that this would happen in the ALU. The ALU will understand now that there is a problem in the arithmetic overflow, and this is in the execution stage. If I have an undefined instruction, this is, I would expect to know that when I begin to decode. So I will fetch the instruction, but I will not know then that there is a problem with that, or if it is undefined or defined. But as soon as I will begin to decode, I will understand that this instruction is not one from the predefined instructions that my system should expect. And at that stage, the ID, I will have, of course, the problem. With input-output service request or the hardware function, this we can think of this as just an interrupts or outside interrupts. And if it is an outside interrupts, I would expect that to happen anytime. And as we mentioned by analogy, that if you are explaining the slides in a lecture that you are giving, you don't know in advance when any of the audience will raise the hand or will basically ask a question. So you don't know in advance when this would happen. And because of that, it can happen any time in this case. Regarding if it is synchronous or not, of course, these two are from inside. So I would expect, yes, they are synchronous. synchronous. These are outside, so I would expect that they are basically asynchronous in this particular case. Also, multiple exceptions can occur simultaneously in a single clock cycle. If this is the case, if I have pipelining overlaps multiple instructions, there is like a simple approach that I can take or handle, that please deal with exceptions from earliest instruction. Suddenly, as an example, there are like multiple problems happen. How I will deal with each one of them. Just simple approach, try one by one. The first that would came, just try to handle that, then the second, and then the third, and so on and so forth. And we begin with the first, just to flush subsequent instructions, and so on and so forth. But with these complex pipelines, unfortunately, this might be difficult to maintain, and we will not go over that particular case, since like it's not that easy to handle exceptions with this kind of complex pipelines, and it is out of the scope of this course. So multiple simultaneous exceptions, assuming with a simple approach. As you can see from here, I have an arithmetic overflow. I have undefined instructions. And as you can see from these, that all of these happens at that particular clock cycle. So I have multiple of these. There is a page fault in the data memory. There is a page fault in the instruction memory. So as you can see, multiple of these. How to solve? Then the hardware will just sort these exceptions. The earliest instruction is the one interrupted first, and I will go to handle that particular things in that particular case. So consider each of the following sets of instructions. Decide the minimum number of stalls needed in each case with and without forwarding. So we need both cases. We assume the same things that we have usually, the 5 stages MIPS, which can change, by the way, in any of the assignments, these 5 stages. Discuss in class that the quality of branches are checked at the decode stage. So the branch is at the decode stage. And this is, by the way, by default, you would assume that if otherwise, if nothing else is specified. Also assume delayed branching, and with this delayed branch mean that the instruction following the branch is always executed before the program count is modified to perform basically the branch. So if there is no forwarding, this is, as you can see from here, add immediate instruction unsigned. And we'll add these two, we'll put the results in T1. And as you can see, I have here my destination is T1, and I'm using T1 here as an RT. So there might be a data hazard. Just like to remind you, if we have stages like that, fetch, decoding, execution, memory, and then write back. If I have this, there is no forwarding. When I would expect that T1 would be updated, I would expect T1 would be updated here, correct? When I write back. But then in order like to get the correct results of T1, so this means that if I will write in the first half, I have to read in the second half. So this means that I have to align this instruction decoder by the write back, correct? I have to align that. If I do this, before the D is just the F, so the F should be here, and then E, M, W. So this means that from here to here, as you can see, I have stalled how many times? 2 times, correct? So from here to here, I have 2 stalls. How about from here to here? This is T4. Am I using T4 here? So of course, I don't need to put any stall, so it is 0, correct? So 2 plus 0 equal 2. So the total number of stalls in this case are 2 stalls. Let's say with forwarding, again with forwarding, F, D, E, M, W. If there is no forwarding, yes, the output will be updated here. But if there is forwarding, I know that I can take the data outside of the ALU, correct? I already knew this information that as soon as I am doing the ALU output, I have already done the addition. And then I can just forward it to whatever, like when it is needed. When I should need something like that. By the execution. So now I would like to do the execution. So this means just give it to the ALU DF. So MW, as you can see from here, there is 0 stalls because I can move from the output of the ALU to the ALU because this is what it needs to do the addition. Then there is no stall at all. And of course, with the second one, there is no stall then since it is not using the T4 at all. Correct? Try to think with the same exact way. So this at the very end, I'm writing to the T0, but none of this T0 basically is here. So from here to here, there is 0 stalls because I don't even need the output of the T0. How about from here to here? Let's check this guy. Again, this is add U. So I have here the F, D, E, M, W. But this T1, I'm using it at that particular location. So there is no forwarding. If there is no forwarding, when I would expect to have this particular data. So this T1 will be updated when? Again, at that particular location. Correct? If I would do that at that particular location, so the D has to align. If the D has to align, F is here, and then E is here, M is here, W is here. Most importantly, right now, I have 2 stalls. How about from here to here? This is T0 and T1. So there is nothing, but how many after the branch? Usually, if you remember, after the branch, I have to one stall, correct? But since I mentioned that you have to assume that you have a delayed branch, and basically delayed branch, you can assume that you have a prediction and your prediction was correct. And if this is the case with the delayed branch, there is no actually stalls at all. And this is different than the usual situation in our case. So again, 0 plus 2 plus 0, 0 plus 2 plus 0. At the very end, the answer should be 2. How about with forwarding? Again, with forwarding from here to here, there is 0 because this T0 is not available here. Then how about the next one? We'll write again F, D, E, M, W. If with forwarding, when these results will appear at this particular stage at the execution. And then if this is at the execution, then what I should do in this case. W, so if this is the case, I just need the decoding to have the results before the decoder. So if I have here, then I can forward it easily. And then I would have, in this case, just one stall. Again, this is 0, 0 plus 1 plus 0 will be equal to 0. How about in this case, as you can see, this is at the very end, I'm using the store word with forwarding. We have shown in the lecture exactly that actually there is 0 stalls because as soon as you will have the things in the memory, then actually you can forward it to the memory because you need to write whatever is here to the memory. So you will just get forwarding from the output of the memory to the input of the memory. We have explained that in details in the lectures, but without forwarding, so if D, E, M, W, then in this case, this is the results. So you will have the D again, 2 stalls in this case. So from here to here would be 2 stalls. How about this? So without forwarding, again, F, D, E, M, W. From here to here, again, 2, because it is appear here, the decoding is there. Then E, the decoding is here. So sorry, so this is the F, 2 stalls in this case. But with forwarding, of course, it would appear here. Then you can do the forwarding. Then there is basically 0 stall in this particular case. So this is just like summarizing all of the answers of such question.